Okay, hi Adam. Sorry you missed the lesson. I know you're having Wi-Fi problems. So what I thought I'd do is I thought I'd give you a quick lesson and go through what I went through with the class. I'm just going to go through it quickly with you and you'll get it from there. Just lost me other glasses, so I'm looking for those. I will post it publicly as well, so the other group can watch it when they get to it, or the rest of the group can watch it back, what we went through. So we, if you remember, I've got my book here. If you remember, we started geometric sequences this year, sorry, and then I abandoned it because I realised that you needed some of the logs that I hadn't done with you. So now that we've covered the logs, we can carry on with geometric sequences. Have a look through the arithmetic sequences. I know you've been doing those questions in your learning timetable, but just make sure you're okay with that. And I'll go through, what I'm going to go through is the two proofs for you for the nth term and the sum of a series. So I'm going to go through those two. I do a quick version of the sum of a series, but I'll show you that and I'll explain what you need to do with that one. Okay. So the first thing that when we started the lesson yesterday, was it Friday? Yeah, it was yesterday. When we started the lesson yesterday, I just asked the question, you know, what is a geometric sequence? So a geometric sequence, for instance, like 2, 4, 8, 16, is, as someone pointed out, the features of it are, sorry, I'm just looking for me other pens. If I've got a red pen, then I'm good to go. Yeah, I have. So the features of it is, of course, the first term, as with the arithmetic sequence, we donate this A. But instead of being a common difference, a gap between each one, you can see that gap is growing, and that's because we are, with a geometric sequence, we times it by a number, and you can see that this one is timesing by 2 each time. So that is the features of a geometric sequence. That's what makes a geometric sequence a geometric sequence, is that you times to get from one to the next in terms. And this is called the common ratio. Okay, so we call this the common ratio, and mathematicians give that a lowercase r. So we're going to use A's and R's. With the arithmetic sequence, we use A's and D's, don't we? A for the first term again, D for the common difference. For a geometric ratio, for a geometric sequence, we use A for the first term and R for the common ratio. Okay, don't ever think about it as dividing. Oh, just blew me nose on that one before. Don't think about it as dividing. So if you get one that goes the other way, so say you get it 16A for 2, you know, the common ratio is still what you times it by, you know, to get there. And of course, the common ratio doesn't have to be an integer, so the common ratio here would be, you know, timesing by a half. So it's always, you know, a multiplier. Okay, right, so that would still be a geometric sequence. Okay, so the first thing that we looked at was the nth term. So let's do the nth term. So a geometric sequence has first term A. The second term, we're going to times that by r, aren't we? So the next term is going to be AR, and then we're going to times it by r again. So it's going to be AR squared, and we're going to times it by r again, and it's going to be AR cubed, and so on and so on and so on. Okay, so here we go. That's the first, that's the second, that's the third, and that's the fourth. And this position line here, you know, is donated, and just checking, Adam, that fits on my screen. Okay, James, I hope you're watching this as well, because you didn't turn up to the Zoom meeting. I don't know why. So anyway, so this is our n value in the nth term sequence, and if you notice here that this number here, okay, this integer here is always 1 less than the position, isn't it? So where you've got position 3, this is 2. So of course the nth term is going to be AR to the n minus 1, whatever this number is, minus 1, and that's the nth term. Okay, so the nth term, and that's the proof for it, okay, the algebra for it. So I'll just let you look at that before I rub it out. So that's the first thing that we did, and we've got the formula. Don't need that. Sorry, that was my work for my year 8. My answers for my year 8. So we've got the nth term is equal to a to the r n minus 1. Okay? I'm just checking that's on screen. So that's the first thing that we did, the first formula that you need. You get, I'm going to go through a couple of questions with you now. I did an EG, and I used the one in the book because it's a nice one, and it's very similar to the ones that you get with the arithmetic. You know, it's the same little problem that you get with the arithmetic sequence. So the question is this is my example. So the numbers 3x and x plus 6 form a geometric sequence. They form a geometric sequence. They are the first 3 terms. Okay, so we've got to find x and find the 10th term. Okay, so find x and find the 10th term. Okay, the book actually says find all the possible values of x. So that's a clue that there's more than one, so we'll have a look at that in a second. Okay, I like this question because you get these on the exam. You also get them for the arithmetic sequence one. So if you remember, when you've got some terms in an arithmetic sequence, so let's go back to this one that we started with as an example. How do you find the common ratio? Well, we can just see that it's timesing by 2, but a way of finding it, if it wasn't blindingly obvious, is to take a term and divide it by the one before. So 4 divided by 2 is 2, and I could do that with any 2 terms. Got it, 8 divided by 4 is 2, 16 divided by 8 is 2. So dividing by the term before will always give you the common ratio. So for this question, the common ratio is going to be x divided by 3, isn't it? But it's also going to be equal to x plus 6 divided by x. Okay, you got it with, we're going to solve that in a second. You get it with the arithmetic sequence where it says, you know, find the common difference, and you go, oh well, that take away that, because that works out the gap between those two, don't you? You go x minus 3 is equal to that, take away that, you know, x plus 6 take away x, and we solve little problems like that if that was a arithmetic sequence. So you had those in the arithmetic sequence chapter, but in the geometric or they're in the same chapter now, aren't they? But in the geometric series section of the chapter 3, you get these sorts of questions as well. Okay, so let's solve that. Okay, so let's get rid of our r, and all I'm going to do is good maths. Is I'm going to move that 3 up there and that x up there, so it goes from being a divide to a times. Okay, so times in both sides by x and times in both sides by 3, and that gives me x squared is equal to 3 times all of that. And I'm not going to put it into brackets, I'm going to multiply it straight out, so 3x plus 18. Okay, then take everything over to one side because we can see that it's a quadratic, and then of course factorize it. Okay, so that's going to be x minus 6, x plus 3, and then solve it is x is 6 and x is equal to minus 3. Okay, so those are your 2 possible values of x. So that means that if we put those in, okay, we've got 3 for our first term, x is 6 if we use the 6, which we're going to actually, which is 6, and the next one is 12, isn't it? So that works with that, and you can see it's an arithmetic sequence, 3 times 2, so the, you know, a is 3, but we saw that anyway, and the common ratio is actually 2 because we're timesing by 2 each time. Okay, and that's the one that we're going to use. That's the one it wants us to use in the book. I think it sort of says where x is positive, okay, as well. All right, this also works actually. If you look at it, it's a strange one. If we put x is minus 3 in there, we get the sequence 3 minus 3, and then if minus 3 plus 6 is plus 3, it's not your conventional geometric sequence, but technically it is a geometric sequence because the common ratio here, it has a first term and it has a common ratio. Can you see that the common ratio for this one is -1? We're timesing by -1 each time, aren't we? So it's going to go 3 minus 3, 3 minus 3, 3. So it's not one of any interest to us. It's not one that we would use and so on. Okay, so we're going to use this one to carry on and solve the next one. You know, the 10th term of that one is going to be -3, isn't it? Okay, but this one here, the 10th one of this one, as we keep going, we're going to use the formula for that, and the formula is A, which is 3, times R, which is, now we know, is 2, and the 10th term is 10 minus 1, which is 9. So that's what we've got to do on our calculator. Okay, so 3 times 2 to the power of 9. Now, I've left my calculator in my school bag, so I'm just going to get that. That gives you a chance to work that out, Adam. Be careful with these, remember. I know that really sort of easy mistake to make. Some students do it, they go 3 times 2 is 6. Okay, but BODMAS, never do that. You have to do your powers first. I'll just go and grab my calculator. And back, it was just outside the door. Okay, so switch it on. So we're going 3 times 2 to the power of 9, and it gives me 1536. Okay, so the 10th term, I'll put that in there now, 10th term is 1536. Okay, so there was that example. So you get that sort of question, so just be aware of that, dividing by the term before to solve little problems. I also want to go through another example with you, and I did with the class as well yesterday, Adam, and that was because I want to show you something that I do it differently than the textbooks, and the way the textbook explains it, and obviously I always think that my ways are better. So here we go. The question is this, the other example is this, EG2. What is the first term in the geometric? So this is the question. So what is the first term that exceeds 1 million? Oops, 6 noughts there. So what is the first term that exceeds 1 million in this series? 3, 6, 12, 24, blah, 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 blah. Okay, so as we keep times in that by, this is common ratio is 2, we can see that, first term is 3, it goes 48, 96, and then it's going to get bigger and bigger and bigger. So what is the first term that exceeds 1 million? Now the book sets it up like this. They go, well, when does AR n minus 1 greater than 1 million? Okay, so that's what they solve. Okay, which is how you find the answer actually. So they've done it right. I don't do that. Okay, so I want to know what value of n is greater than 1 million. But the way that I always do these is I say what value of n is equal to 1 million. Now remember, the n is only either the first term or the second term or the third term or the fourth term and so on. So it can only be a whole number. And by this, unless one of the terms is exactly 1 million, which I can tell from this series it's not going to be, I'm going to get a decimal. So once I get that decimal at the end, I just go back to checking real life, to thinking about it in a real life situation. Okay, but I find it easier than dealing with those greater and less than signs. And there's a little bear trap with those as well, that I've come across in the past and students have come across. So I'll tell you about that, and I told the class about that yesterday. So I'll talk about that in a minute, but let's do this one. So we're looking at what value of n gives us, the millionth, a term that is 1 million. Okay, so we can see that A is 3, and we're going to times that by are the common ratio of n minus 1 is equal to 1,000,000. And it's the value of n that we want to find in this. So the first thing that we're going to do is we're going to divide both sides by 3. Okay, if I divide by both sides by 3, my next line would be that is equal to that over 3. But with modern technology of a whiteboard, a finger and a pen, I can just do that. Okay, now this is where we use logs, and this is why we cancelled doing geometric sequences and came back to it at a later date. The log of this, now log, I'm a proper mathematician, so we don't use log, we use ln, the ln button, okay, of 2 to the n minus 1 is equal to ln of 1,000,000 over 3. I've got to write this out loads of times now. Okay, and this is why we use logs. Remember that rule of log? The reason that we have rules of logs is because it allows us to solve problems with powers in, and this power now, the best rule of log ever, innit? Love it, lovely, is this moves down, this n minus 1 can move down. That's why we have it. That's the rule that you use more often than not. That's the really handy one. Is equal to ln of 1,000,000 over 3. 1, 2, 3, 4, 5. And you're going to miss one out, just be careful when you're doing these. Divide both sides by ln 2, and now we've got n minus 1 is equal to ln of 1,000,000 over 3 divided by ln 2. Okay, and then we're going to add 1 to both sides, and power, you know, because of technology, I can just go add 1 to both sides and add it on there, and that's my value of n. That, all that garbage there is just a number, isn't it? So on my calculator, let's just solve that, and I get ln of 1,000,000 over 3, 1, 2, 3, 4, 5, 6 over 3, closing my brackets there. I think I'm doing this, I'm getting good with these calculators now. Ln of 2, you know, when I was at school we had log tables. So there we go, you can sort of see that there it is. Okay, and we're gonna, and let's add the 1 to it. Yes, look at that, amazing, isn't it? Modern technology. There we go, and that gives us the value of n, which is 19.34. Okay. Okay, so that's the term number, and of course there isn't such thing as a 19.34 term. It's either the 19th term, isn't it, or the 20th term. Okay, now the 19.34 term gives us that million. So in other words, the 19th term is going to give us a term that is just a bit less than 1,000,000, and the 20th term is going to give us a term that is more than 1,000,000. That's the first one that exceeds 1,000,000. So if the question was, what is the first term, you know, that does not, the biggest term that does not exceed 1,000,000, then the answer would be the 19th term. If the question like this one is the first term that exceeds 1,000,000, then it's the 20th term. And that's our answer. Okay. Right, greater and less than. Why don't I like using them? Just be careful, there will be a question on one of the learning timetables that will come up this next year, because I know, because I've written them and I've put it on. And I got caught out by it. It's one of those ones where you have to show that, and you're rearranging one of these, you know, equations like this in a geometric sequence problem, and it's done with, you know, the greater and sort of like less than sign, so you're doing that all the way through. And when you get to the end, what you've got to show, the greater or less than sign is the wrong way around to what you've kept it sort of going all the way through. Okay, and I was staring at that for ages before, and students would question me about it as well. Okay, and some of them just looked at the mark scheme and saw it was the other way around, just turned it round and didn't know why they turned it round. Okay, so just in case you come across it, in fact I'm saying in case you come across it, you will come across it. Okay, if you remember from GCSE, when you're solving an inequality, say you have something like, you know, you end up with minus 2x is greater than 10. Okay, what you can do with inequalities is to solve that, you can times through by -1, can't you? If it was an equal sign, that's what you would do, and you could go, so you'd have 2x is -10 on this side. But do you remember that little rule? If you do that, if you times by a negative number when you're solving inequalities, you have to flip the sign round, okay? And then you'd have x is less than -5. Otherwise, you get the wrong answer, okay? It doesn't actually work. So you've got to remember that if you times in by a negative number or dividing each side by a negative number with inequalities, you've got to flip the sign round. I sort of get round that with when I'm teaching me bottom set year 10s and we're doing inequalities. If they get to that stage, I just get them to do it by adding 2x to both sides, okay, and then taking 10 off both sides. So I don't have to teach them that rule, and it's one less thing for them to think about, and they get that. And of course, you can see then when you divide by 2, that is effectively flipped around itself, isn't it? But you've done it by moving these over. So that gets around the problem. But you've got to be careful that when you're doing the maths for this, because they contain logs, if you had an equation where an inequality where you had something like ln of a half, you're looking at that, but what you may not realise that the ln of anything less than 1, between 0 and 1, the log of a fraction is negative, okay? So the log of anything between 0 and 1, the ln of anything between 0 and 1 is negative. So if you are dividing both sides by, like we did it on that one, we divided both sides by ln 2, okay? But had it been ln a half, we would have had to flip the signs round from that to that, because we're effectively dividing by a negative number, okay, when we move it down. And you don't realise that because you're not actually physically looking at a minus sign, are you? But that, as an entity, is negative. Adam, that's going to come back to you, so you've got to remember that as well, okay? Which is why I try to use equal signs and then just change at the end. All right? Okay. So that you can get on, you can do some of the questions from exercise 3C, but I'm going to go straight on with you now because I did with the class, and I'm going to look at the sum of a sequence. Now, what I will say about this is on the old A-level, and I imagine the new A-level is going to be the same, that you will have to be able to prove the two formulas, the formula for the sum of an arithmetic sequence and the formula for the sum of a geometric sequence. Now I show you the shortened version of those, and what I will say is that they don't put it on every year, or they never used to put it on every year. They used to put it in rotation and put one of them on every 5 years. And the reason they do that is if they put it on every year, everyone would just learn it by rote, wouldn't they? And then they just regurgitate it and obviously get the 3 or 4 marks for it. So it wouldn't really be testing you mathematically then. So they just used to leave it about 4 or 5 years. So yeah, follow what I'm doing now. But I'll remind you before the exam, don't hold it in your brain, forget it, that's absolutely fine as long as you know the formula, okay? But just before the exam, I just get my classes always just to go over the proof for them, just in case they crop up on the exam, and then you can just regurgitate it and stick it in, okay? So I'll show it to you so you see the proof. It's my shortened version. It's much easier to understand than the book with all of the n-1s and n-2s in. My methods are always better, as you well know. Okay, so I'm just going to go through it with you now. Okay, so what I do is I pose the question, and I'm going to look at the sum of 4 terms, not n terms, which we need, but the sum of just 4 terms. Okay, and if you do the sum of 4 terms, I'm going to do a capital S for the sum, and 4 for 4 terms. So the sum of 4 terms, of course, is A plus AR plus AR squared plus AR cubed. That is the sum of 4 terms. Okay. Now what we do is this is the proof. If we times everything by R in this equation, okay, we get R times the sum of 4 terms is equal to AR plus AR squared plus AR cubed plus AR to the power of 4. Okay. And if I shufty everything along, okay, so what I'm going to do is I'm going to move, I did that first, but I knew that I was going to move them along. I just lined them up with my So if I go r times the sum of 4 terms, now I'm going to move these along, so I'm going to go AR, I'm going to put the AR there, and the AR squared there, and the AR cubed there, and the AR to the power of 4 there. Okay, can you see that I've just moved them along? And now if I just rub that line out, because I don't need that one, I've got it there, just shift it along. You can see my intention here, I've lined those up. Okay, and what I'm going to do is I'm going to do a simple takeaway. I'm going to do the top line, take away the bottom line. So that take away that, so the sum of 4 terms, take away r times the sum of 4 terms, is equal to all of this, take away all of that. And a take away nothing, just leaves me with a, but ar take away the ar squared take away ar squared, 0, that take away that is 0, 0 take away that would give me minus ar to the 4. Okay, yeah. Now if we factorise both sides, okay, we can go that the sum of 4 terms is 1 minus r minus r to the 4. Okay, so we factorise both sides, and then because we've cheated and done a 4 in there instead of n, we've got to make a statement now. What is true for 4 terms is true for n terms, because if we'd use 5 terms it would just be the same, but there'll be a 5 in there, 6 terms, but we've used n terms. So now we've got that, the sum of n terms, there it is. Okay, and then you can see what we're going to do, we're just going to divide by 1 minus r. So the sum of n terms is a 1 minus r to the n over 1 minus r, and there it is. Okay, and that's the formula for the sum of n terms of an arithmetic sequence. Remember it as r 1 minus r to the n over 1 minus r. They go handily, they go the same way. Okay, and there's one little quirk, well there's a couple of little quirks of this actually, and I don't know whether you noticed, but if I rub that out now that you've got that and you've seen it, okay, I'm just going to rub that line out. Of course, when we got to there, we could have, if we wanted to, have taken away the other way around. So if I write this one underneath it, so this one here, if I write it underneath ar squared ar cubed, so I've just moved this one down and written these two lines the other way around. I've now got them that way round, and I can do the takeaway here. And if I do the takeaway here, I've got r times r s4 minus s4 is equal to, and that's minus a, goes plus a r to the 4. And you can see here when I switch my n and factorise that, you know, and obviously write the plus a there, that would make more sense, but then I factorise it, change this to n, I end up with a to r to the n minus 1 over r to the minus 1. I don't need the brackets around that, so I end up with that. These two are the same thing. They're the same mathematically, they're the same formula. If you times top and bottom by minus 1 there, because it's a fraction, you'd get, you know, rearranged it, you'd get this. Okay, that's all it is. So they're the same thing. So you can remember either one of those. In the lesson I posed the question, I think Ollie gave me the right answer to this. I posed the question because I used both of these, and I said, when might I use this one or when might I use that one? And of course the answer is, depends on your value of r. If r, the common ratio, is a whole number greater than, or a number greater than 1, you know, say it's 5, I would use this version, because 5 take away 1 is 4. I've got a positive number on the bottom, and the maths is just a little bit easier. Whereas if I use this one, I've got 1 take away 5, which is minus 4, and then I've got to divide through by minus 4, and it's just, you're just dividing through by negative numbers, and you've just got to be a little bit more careful. Okay, so I tend to use this one. If I've got a fraction, the common ratio is a half, okay, then I'd use this one, because 1 take away a half, you know, is a half, or and so on. So you've still got a positive number on the bottom. Okay, all right. So any fractions, you know, I use this one here. Okay, just yeah, a little trick again. You know, say for instance the common ratio was say 3/4 or something like that. No, let's go 1/4, and you were using this one. Yeah, if you were using this one, you go 1 take away 1/4, wouldn't you? You'd have 3/4 on the bottom. Okay, so just remember how you divide by 3/4. Think of it as, back to GCSE, dividing by 3/4 is the same KFC, keep the first, flip the second, and change, divide to times. So dividing by 3/4 divided by any fraction is the same as timesing by the reciprocal of that fraction. In other words, invert and multiply. So when you get that, I always immediately, you know, change it to timesing by 4/3. So the 3, what's on top goes on the bottom, or stays on the bottom, and the bottom goes to the top. So just a little quick flip and you're in business, okay, for that. Okay, that's where we got up to. I did mention that the next lesson that I do, which I'm going to do in class with you, is the sum of infinity, because we looked at that sequence, didn't we? Okay, and you can see here that you're timesing by a half each time, and if we carried on with this one here, it's another quirk of these, you can see that this is getting smaller and smaller, and actually, you know, once you get to the millionth or the 10 millionth or whatever, the infinite term is infinitely small, and once it's infinitely small, it's 0. You're not really adding anything more on. So these sequences, geometric sequences, when the common ratio is a fraction less than 1 or greater than -1, then it has a limit to the size of it, the amount it sort of reaches. So it has a sum to infinity. Okay, this particular sequence, out of interest, it never gets bigger than 32. So with infinite number of terms, it reaches, you know, a total of 32. You can see it's homing in on that. 69, it's 24, 28, 30, 31, 31 and a half, 31 and 3/4, 31 and 7/8, and so on and so on and so on. But it reaches at infinity only 32, and there's a formula for that. Just a simple variation of the ones that we've just looked at. Okay, but I go through the proof of that in next lesson. Okay, so have a go at exercise 3C and 3D. I think they are the next two in that book. Is 3D, yeah, is the sum of, yeah. Okay, so have a go at 3C and 3D before the next lesson. And I can't remember whether I've got you next Thursday or the week after. So the sum of n terms is going to be, you've got a choice. You've got a times r to the n minus 1 over r minus 1, or the sum of n terms is a 1 minus r to the n over 1 minus r. Once you've done them a few times, they are easy to remember. Okay, I think you get given them on the formula booklet, but it's good to remember those. Okay, that was the lesson that you missed. Okay, I did sort of go through exactly the same with the class. Obviously I went through it, Adam, a little bit sort of slower, and asked a few questions as well. We were all on Zoom, so it was a bit of a surreal experience, but lovely to see all of your faces. Okay, I'll put that public because the other group can watch it, and my group, our group, can sort of go over the lesson again. Okay, and I hope that helps you. So that was from page 66 onwards, Adam. All right. Okay. See you soon, mate. Okay. Hopefully this week, actually. And I haven't checked the learning timetables for this week yet, so I'll go over those. I might sort of still do a video actually for the third one. Okay. Bye bye now.